In this video, we'll build on our previous probability work to develop the idea of expected value, and we'll see how we can use expected value to help make decisions. I'll start by defining expected value. A random variable, denoted by capital X, represents the possible values of a random event. We can think of a random variable as ranging over the values in the sample space for a random process. Then the expected value for a random variable is a theoretical long-run average value, that is the average value of x over many trials. Before working through calculations for expected value, let's first contextualize it with an example. We've previously discussed flipping coins as a classic example of a random process. Another is rolling a die. For this example, the random variable would be the outcome of the die roll. The variable could take on any of the values 1 through 6. The expected value for this variable is then the average value of a roll over many different rolls. A natural question is if and how we can compute expected value without just running through many trials of the random process. We can, using the underlying probability model. In this formula, little x represents one of the specific values for the random variable. Or, in other words, one of the values in the sample space. P of capital X equals little x means to take the probability when the random variable has the value little x. Then this probability is multiplied by little x, and all such quantities are summed. Let's compute the expected value for rolling a die. Here, I've included the formal probability model. The sample space is just the numbers 1 through 6. These represent the possible values for the random variable x. Since each of these 6 numbers is equally likely to be rolled, the probability of each is 1 over 6. Now we're ready to compute the expected value. So we can start with x equals 1, which has a probability of 1/6. Next, we let x equal 2. And again, we have 2 times 1 over 6. We continue this process for all values in the sample space. Computing this, we get 3.5. That is, if we rolled the die many times, the average would be 3.5. Let's look at a more interesting example, a game of chance. The rules are as follows. You draw a card from a deck. If you get a red card, you win nothing. If you get a spade, you win $5. For any club, you win $10, plus an extra $20 for the ace of clubs. Understanding the expected value could help you understand how much you should be willing to play for the game. To compute the expected value, we can start by creating a probability model. Here, I've identified the 4 different categories involved in the gameplay: red, spade, non-ace club, and ace of clubs. This corresponds to winnings of 0, 5, 10, or $30. This is the sample space. Next, we can determine the probability of each outcome. There are 52 cards in a deck, and half, or 26 of them, are red cards. Therefore, the probability of randomly drawing a red card is 26 out of 52. 13 out of 52 cards are spades, so there's a 25% chance of this outcome. For clubs, we treat the ace separately from the other clubs since it has a different reward. 12 out of 52 cards are non-ace clubs, and there is 1 ace of clubs. Now here's the expected value calculation. We take each reward possibility, multiply it by the probability that it occurs, and add up all the values. This gives an expected value of 4.13. In other words, if you were to play this game many times, you could expect to win an average of $4.13 per game. The previous example gives us some insight into how expected value could help us design gambling games. But how do they help us make decisions? Let's look at one final example where we can use expected value to do just this. A hurricane at category level 3 or above is considered a major hurricane and involves sustained winds above 111 miles per hour. Evacuations of hurricane-prone communities can take days, so that decisions about whether or not to evacuate have to be made before meteorologists can be certain about whether or not the hurricane will make landfall in a given region. How do government leaders decide whether or not to issue an evacuation order? One consideration is the number of fatalities that might result from the various options. If the hurricane hits the city, scientists predict that 1,500 people will die if there is no evacuation order, but only 500 people will die if there is an evacuation order. However, the evacuation process itself is chaotic and may result in some deaths. Suppose that if there is no hit by the hurricane, 100 people are still predicted to die from the evacuation process, whereas if there was no evacuation order, there would be no additional deaths. If there's a 70% chance of the hurricane hitting, is an evacuation order the right move? We can compute the expected number of fatalities for both an evacuation scenario and a no evacuation scenario. First, I'll note that the probabilities of each outcome for the random variable. We get p equals 0.7 for a hit and p equals 0.3 for no hit. To compute the expected value for the evacuation scenario, we use the values in the first row. And so we have E of x is equal to 500 times 0.7 plus 100 times 0.3, which comes out to be 380. That is, if this scenario were to repeat many times, with the hurricane sometimes hitting and sometimes not, on average 380 people would die during an evacuation. To compute the expected value for the no evacuation scenario, we use the values in the second row. Here we have E of x is equal to 1,500 times 0.7 plus 0 times 0.3, which comes out to be 1,050. If this scenario were to repeat many times and there was no evacuation, with the hurricane sometimes hitting and sometimes not hitting, on average 1,050 people would die. Based on this reasoning, evacuation results in lower loss of life on average and suggests this is the better policy choice. The reasoning I shared in the previous example is an example of trying to maximize expected value. We can generalize this to a general process for decision making. That is, when making a decision between uncertain alternatives, choose the strategy that has the preferred expected value.